Morning. This week's lesson is an introduction to calculus. We're going to cover the chapters 24, 25, and 26. We will talk about limits, continuity of functions, and differentiation. First, limits. Let's consider this function, x squared minus 1 divided by x minus 1. This function is not defined when x is equal to 1, because otherwise the function would be divided by 0. But it's defined for every other value of x in the real numbers. The graph of this function looks like this. It's a straight line, except we have a hole when x is equal to 1. And I want to ask the question, how does this function behave if x is close to 1? We can look at some values of x close to 1 and calculate f of x. For example, if x is equal to 0.9, we can calculate that f of x is equal to 1.9. If x is equal to 1.1, then we can calculate f of x is equal to 2.1. Or perhaps we want to look closer to 1. Perhaps we want to look at 0.99 and 1.01. Now, it looks from these values that if x is close to 1, then the function is close to 2. Let's look a little bit closer. What about 0.999 and 1.001? Again, x is close to 1 and f of x is close to 2. From these numbers, it looks like if x is close to 1, then f of x is close to 2. In mathematics, we have a way of writing this. We call this a limit, and we write this as the limit as x tends to 1 of f of x is equal to 2. When x gets closer and closer to 1, f of x gets closer and closer to 2. Back to the same function again. Note that for this function, the limit as x tends to 1 of f of x is equal to 2, but the function is not defined when x is equal to 1. Let's look at a different function. Here's the function g, which is defined to be x squared minus 1 divided by x minus 1 if x is not equal to 1. Same formula as for f, but now we're defining g to be equal to 1 if x is equal to 1. Then again, if x is close to 1 but not equal to 1, then the function is close to 2. So we can write that the limit as x tends to 1 of g of x is equal to 2. One thing to remember here is when we have x arrow 1, this means x is close to 1 but x is not equal to 1. And for this function, the limit is equal to 2, but g of 1 is not equal to 2. A different function, this function I'm calling h. H is equal to x plus 1. What is the limit as x tends to 1 of h of x? Again, this is equal to 2. And this time, h of 1 is equal to 2. This time, the limit as x tends to 1 of h is the same as h of 1. Let's look at some examples of easy functions. Suppose, first of all, we look at the identity function. F of x is equal to x. And then we can ask, what is the limit as x tends to some number x0 of x? And from the graph, we can see that this must be x0. Plus, we have a constant function. Let's say a function which is always equal to 13. What is the limit as x tends to some number x0 of this function? The limit of a number, in this case 13, is always equal to that number. Sometimes functions do not have limits. I'm going to show you two functions, functions u and function v. Function u is equal to 0 for negative x and equal to 1 for non-negative x. Function v is equal to x for non-positive x. Sorry, function v is equal to 0 for non-positive x and equal to sine 1 over x for positive x. First, let's look at u. I want to point out that the limit as x tends to 0 of u of x does not exist. To understand this, let's suppose that x is close to 0 and x is negative. In other words, let's suppose x is here, close to 0 but less than 0. Then the function here is equal to 0. Alternatively, let's suppose that x is close to 0 but x is equal to 1. But then the function is equal to 1. But 0 and 1 are not close together. We can't find some number that the function is always close to if x is close to 0. So the limit as x tends to 0 does not exist. Here's a graph of the function v. Again, the limit as x tends to 0 of v of x does not exist. And this time the reason is because the function is going up and down too quickly, there doesn't exist some number that the function is always close to. Sometimes the function is 1, sometimes the function is 0, sometimes the function is -1, and sometimes in between. There doesn't exist one particular number that the function is always close to. So this function does not have a limit as x tends to 0. We have some rules which help us find more sophisticated limits. Let's suppose capital L, capital M, C and K are numbers. Let's suppose that f and g are functions. Let's suppose the limit as x tends to c of f of x is equal to L, and the limit as x tends to c of g of x is equal to M. The first rule is called the sum rule. The limit of f plus g is equal to L plus M. Anytime we have the limit of two functions added together, we can just separate them and calculate the limits separately. Likewise, we have a rule called the difference rule. This is the same as the sum rule, except with a minus sign instead of a plus sign. We have a rule called the constant multiple rule. The limit of a number k multiplied by a function f of x is equal to k multiplied by L. In other words, anytime we have a number k inside the limit, we can take this outside of the limit. The product rule. If we have a limit of two functions multiplied together, then we can separate this into two limits, calculate the limit of f, calculate the limit of g, and then multiply them together. We can also do the same if we have f divided by g. The limit of f divided by g is equal to the limit of f divided by the limit of m. But we have to be careful here. One extra condition. This is true as long as m is not 0. We have a rule called the power rule. The limit of f to the power n is the same as L to the power n. That makes sense. And we have a root rule. The nth root of the function f, and then take the limit, is the same as the nth root of capital L. as long as, and to be careful, as long as this root exists. Next example. Find the limit as x tends to 2 of x cubed plus 4x squared minus 3. First, I can use the sum and difference rules to split this up into 3 easier limits. The limit of x cubed plus the limit of 4x squared minus the limit of 3. This number 4 is a constant. Using the constant multiple rule, we can take the 4 outside of the limit, and then we get the limit of x, sorry, one part I missed. We could also use the power rule on this x cubed to take this outside, and on this x squared to take this outside. And then we get the limit of x all cubed plus 4 times the limit of x all squared minus the limit of 3. And of course that's 2 cubed plus 4 times 2 squared minus 3, or 21. Find the limit as x tends to 5 of x to the power 4 plus x squared minus 1 divided by x squared plus 5. Here we have a function divided by a function, so we start by using the quotient rule. We start by writing this as the limit of x to the power 4 plus x squared minus 1 divided by the limit of x squared plus 5. Then we can use the sum and difference rule to break this up into easier limits. Use the power rule to calculate each of these easier limits, and we get our answer 649 divided by 30. If I give you an exam question and I say, you must say which rules you're using, then I would expect something like this. At each step, I expect you to say which rule or rules you are using. Those rules are fine, but there's an easier way to find the limits of polynomials or rational functions. If capital P is a polynomial function, then we always have that the limit as x tends to c of p of x is equal to p of c. If we have a rational function, p of x divided by q of x, where p and q are both polynomials, and as long as q of c is not 0, then the limit as x tends to c of p of x divided by q of x is equal to p of c over q of c. For example, the limit as x tends to minus 1 of x cubed plus 4x squared minus 3 divided by x squared plus 5. We don't need to use the rules. We don't need to use the quotient rule or the difference rule or the sum rule, etc. anymore. We can just use the previous theorem. Because we have a rational function and because the limit of the bottom is not 0, we can just replace x by the number minus 1 and then calculate that this is equal to 0. That's great if q of c is not equal to 0. But what can we do if q of c is equal to 0? How do we then calculate the limit as x tends to c of p of x divided by q of x? For example, calculate the limit as x tends to 1 of x squared plus x minus 2 divided by x squared minus x. We can't just use the previous technique of putting in the number x equal to 1, because then we would get 0 divided by 0. And this is not a number, this is undefined. In mathematics, we never want to get 0 divided by 0. So instead, we need to be smarter. Instead, we're going to try to factor x squared plus x minus 2 and x squared minus 1. The first thing to remember is when we do a limit, x tends to 1, we're interested in numbers of x, values of x which are close to 1 but not equal to 1. So in our calculation, it's always going to be okay to assume that x is not equal to 1. Then we can factorize our function into x minus 1, x plus 2 divided by x, x minus 1, or x plus 2 divided by x. Now we have a function where the limit of the bottom is not 0, so we can use our technique and replace the value of x by 1 to calculate that this is equal to 3. We have a theorem called the sandwich theorem. Let's suppose we have 3 functions, a green function, a blue function, and a red function. And let's suppose that we know that the green function and the red function have the same limit at c. And let's suppose that we know that the blue function is squashed or sandwiched between the green function and the red function. Then the theorem tells us that the limit of the blue function must be the same here. Squashed from the bottom by the green function, it's squashed from the top by the red function, so it must be the same. Precisely. If we know that the inequality f less than or equal to g less than or equal to h is true for all x close to c, we don't care what happens a long way away from c. Over here on the left, we don't care what happens. Over here on the right, we don't care what happens. We only care that this inequality is true close to c. And let's suppose that we know that the limit of f and the limit of h are the same. Then the theorem says the limit of the function in the middle must also be equal to this same number. We can use the sandwich theorem to calculate limits like this. We're told in the question that this inequality is true for all x close to 0, but not for x equal to 0. And then we're asked to calculate the limit as x tends to 0 of x sine x divided by 2 minus 2 cos x. We're going to use the sandwich theorem. We're going to calculate the limit of the function on the left, the limit of the function on the right, and then we're going to use the sandwich theorem. For the function on the left, we can calculate that this limit is equal to 1. The limit of the function on the right is also 1, of course. So by the sandwich theorem, the limit of the function in the middle must also be equal to 1. A similar theorem. Let's suppose we have 2 functions. And let's suppose g is the bigger function. Here's g, and some other function f. And let's suppose that we know that close to c, g is bigger than f. Let's suppose that the limit as x tends to c of f and g exist. Then we can say that the limit as x tends to c of f must be than the limit as x tends to c of g. And like with the sandwich theorem, we're only interested in if the inequality is true close to C. Over on the left, we don't care what happens. Over on the right, we don't care what happens. We only care what happens close to C. Now I'm going to take a 5-minute break. And now let's continue by talking about continuity. The key idea here is, when can we draw the graph of a function without lifting our pen from the paper? If we wanted to draw a function like this, we can put our pen on the paper on the left side. We can draw the graph all in one go without having to lift our pen. If we can draw a function without lifting our pen off the paper, then we have a continuous function. If instead, when we're trying to draw the graph of a function, we start on the left, we draw the function, but then we have to lift our pen off the paper, move our pen to a different point, and then put it down and keep on drawing, then we have a function which is not continuous. Let me be more precise. A function is continuous at some point C if these three rules exist. We need f of c to exist. We need the limit as f of x tends to c of f. So limit as x tends to c of f of x to exist. And we need these two numbers to be the same. If a function is not continuous at a point C, then we say that the function is discontinuous at C. And we say that C is a point of discontinuity of f. For example, have a look at this function. I'm not giving you the formula, I'm just showing you the graph of this function. Where is this function continuous? Where is this function discontinuous? First, I want to look at c equal to 0. Is f of x continuous here? The answer is yes. Why? Because the limit as x tends to 0 of f of x exists. F of 0 exists, and both of these numbers are equal to 1. All three rules are satisfied. What about between 0 and 1? Pick some value of c between 0 and 1. Let's say c is just here. Is f continuous at this value of c? The answer is yes. Again, because the limit exists, f of c exists, and they are the same number. What about that 1? Is the function continuous at 1? The answer is no. It's not continuous because the limit does not exist. If we only looked at the left side, the limit would be equal to 0, but if we only look at the right side, the limit would be equal to 1. 0 and 1 are different numbers. The limits, just looking at each side, are different, so the limit doesn't exist. Between 1 and 2, and between 2 and 4, again, the function is continuous because the limit exists, f of c exists, and they are the same number. What about at 2? Is the function continuous at 2? And the answer is no. The limit exists. The limit exists and is equal to 1. F of 2 exists, and f of 2 is equal to 2. But these are different numbers, so the function is not continuous at 2. What about at 4? The function is not continuous for the same reason. The limit exists and is equal to 1. If x is close to 4 but not equal to 4, then the function is close to 1. That's true. F of 4 exists and is equal to a half. but these two numbers are not the same, so the function is not continuous here. Next example. F defined on the closed interval from -2 to 2 with the formula f of x is equal to the square root of 4 minus x squared. The graph of which looks like half a circle. This function is continuous for every point between -2 and 2. The function g, which is defined for all real numbers, g is equal to 0 for negative x, g is equal to 1 for non-negative x. Where is this function continuous? Where is it not continuous? Between -infinity and 0, I could draw this in one go. I could put my pen on the paper, I could draw the function, and draw this whole piece in one go without having to lift my pen. Then at 0, I have to lift my pen up from 0 to 1, put my pen back on the paper, and then draw the second half of the function. I have to lift my pen at one point. I have to lift my pen at 0, so the function has a point of discontinuity at 0. The function is continuous everywhere else. This function, the function is continuous between -infinity and 1, between 1 and 2, and between 2 and infinity. This function has points of discontinuity at c equal to 1 and c equal to 2. If we have a function which is continuous at every point in its domain, then there's a quicker way of describing it. Instead of saying it's continuous at every point, we just say that it's a continuous function. Theorem. If f and g are continuous at a point c, then f plus g, f minus g, k multiplied by f for some number k, f multiplied by g, f divided by g, as long as f of c is not 0, f to the power n are also all continuous at c. For the nth root, we have to be a little bit careful. Don't worry too much about this. This is just me being careful. If the nth root of f is defined on some small open interval around c, then the nth root of f is also continuous at c. For example, every polynomial is continuous. X is continuous, for x to the power n is continuous by the previous theorem. That means a number multiplied by x to the power n is continuous by the previous theorem. Then we have continuous function plus continuous function plus continuous function plus continuous function, etc. The previous theorem says we can add continuous functions together and we still have a continuous function. For a rational function, if p and q are polynomials, and if q of c is not 0, then p divided by q is also continuous at c. Another example, sine and cos are continuous. We can also look at the composites of two functions, g composed with f. We might imagine functions as arrows going from a set to a set. Let's suppose f is this blue arrow, which maps from the point C to the point f of C. And then let's suppose that after we do f, we do g. G is this green arrow, which maps from the point f of C over to the g of f of C. If we know that f is continuous at c, and we know that g is continuous at f of c, then we know that g composed with f is continuous at c. For example, show that the square root of x squared minus 2x minus 5 is continuous on its domain. By the previous theorem, which in the lecture notes is theorem, it has a number, we know that the square root of t is continuous. We know that x squared minus 2x minus 5 is continuous because all polynomials are continuous. Therefore, our function, which is g composed with f, is also continuous. And that's all we need to say. Show that x to the power of 2 over 3 divided by 1 plus x to the power of 4 is continuous. By the theorem, x to the power of 2 over 3 is continuous. 1 plus x to the power of 4 is continuous because all polynomials are continuous. 1 plus x to the power of 4 is always not equal to 0. If we drew the graph, it would look something like this. Always positive. So then we're done. We have a continuous function divided by a continuous function which is not 0. We must have a continuous function. Next theorem. If g is continuous at a point b, and if we know that the limit of as x tends to c of f of x is equal to b, then if we try to calculate the limit of g of f of x, we can take the function g outside of the limit. Or to say this another way, limit and g, we can swap their places. So long as our functions are continuous, we can swap g and limit. For example, let's suppose I want to calculate the limit as x tends to pi over 2 of cos of 2x plus sine of 3 pi over 2 plus x. Cos is continuous, so we can swap the places of limit and cos. Instead of writing limit and then cos, we can write cos and then limit. And then using the technique again, sine is continuous, so instead of writing limit and then sine, we can swap the positions of limit and sine, and instead we can write sine and then limit. Using these rules, we can calculate that this limit is equal to minus 1. I'll leave this calculation for you to check in the lecture notes later. Our final chapter of today's lesson, which will take maybe 30 minutes or so, is about differentiation. This road sign, which I imagine you've seen while you're driving, so means the road is going up, and it tells us that the 3% tells us how steep the road is. What this means is, if we travel forward 100 meters, the road goes up 3 meters. The road goes up 3%. In mathematics, we have a slightly different way of writing this. We say that the slope of this green line is 3 divided by 100. Instead of writing 3%, we write 3 divided by 100, or 0.03, or however you want to write this. In general, if I had a green line like this, and if I could draw a triangle underneath the green line, if the base was horizontal with length A, and the height of the triangle was vertical with height B, I would say that the slope of the green line is B divided by A. Some examples. The slope of this line is 3 divided by 3, or 1. The slope of this line is 4 divided by 2. This line is going down. To indicate that it's going down, we say that the height of the triangle is now -2. And then we say that the slope is -2 divided by 4. What about if we have a function? This is not a straight line, this is a curve. How could we describe the slope of a curve like this? I suppose I wanted to know the slope of this curve at the green point, where x is equal to x0. What we can do is we can draw a green line which just touches the blue curve at this point. Such a curve is called, such a line is called a tangent line to the curve. And then we say, then we can measure the slope of the green line. We know how to do this. We can use a triangle. The slope of the green line is b divided by a. And what we say is the slope of the blue curve when x is x0 is the same as the slope of the tangent line just here. So if we know the slope of the tangent line, then we know the slope of the blue curve. But how can we find the slope of the tangent line? Look at some examples first. Let's suppose we have the function x squared. I lost connection, but I'm back now. I hope you can hear me now. I'm interested in the slope of the function y is equal to x squared at some points. Let's suppose first we let x be equal to 1. We can draw the green line. We can measure the slope of the green line, and it turns out that the slope is equal to 2. Or I'm interested in the slope when x is 0. This time I'm using an orange line. The slope of this line is 0. Or if x is equal to 2, now I'm using a red line. The slope of this red line is equal to 4. We should be asking, how can we calculate the slope of a tangent line if we just know the function? Let's look at this graph again, just some function f of x. I want to calculate the slope of the tangent line, and without plotting the graph and getting the ruler out and measuring, without drawing a triangle and measuring this, how can we do this? There is a line that we can measure the slope of. We can measure the slope of this orange line. Let's suppose the orange line connects these 2 points together. The point on the graph where x is equal to 0, and the point on the graph where x is equal to x0 plus h for some number h. Then we have a triangle here. And we can measure the width and the height of this triangle. The width of this triangle is h, and the height of this triangle is f of x0 plus h minus f at x0. So we know the slope of the orange line. The slope of the orange line is the height of the triangle divided by the width of the triangle, or f of x0 plus h minus f of x0 divided by h. We don't want the slope of the orange line, we want the slope of the tangent line. But look what happens as we make h smaller. When h gets smaller, slope of the orange line gets closer and closer to the slope of the green line. We can say that if h is very, very small, then these two lines have approximately the same slope. We can say that the slope of the tangent line is approximately equal to the slope of the orange line, which we have a formula for. In fact, as h gets smaller and smaller, but not equal to 0, the slope of the orange line gets closer and closer to the slope of the tangent line. But we know what closer and closer means. This means limit. We are interested in the limit as h tends to 0 of the slope of the orange line. This is equal to the slope of the green line, which we've said is the same as the slope of the blue graph. The slope of the blue graph at the point x0, which is also called the derivative of f at the point x0, is defined to be this limit if this limit exists. We start with a function f, and then we calculate its slope or its derivative, and then we need a new way to write this. We write this as f prime. For example, let's suppose g of x is equal to 1 over x. Calculate the derivative or the slope of this function at a point where x is not equal to 0. We start with the formula in the definition. The derivative of g at the point x0 is the limit as h tends to 0 of g of x0 plus h minus g of x0 divided by h. G of x0 is just 1 over x0. We also need g of x0 plus h. This is the same function, but instead of x0, we have x0 plus h. So this must be 1 divided by x0 plus h. We need to simplify this before we can take the limit. Because if I want to do a half plus 1/3, as we learn in primary school, what we do is we write this over the same denominator. We write this as 3 divided by 6 plus 2 divided by 6. We can use the same idea here. Instead of 1 over x0 plus h, we can write this as x0 divided by x0 plus h. And instead of 1 over x0, I can write this as x0 plus h divided by x0 plus h. Or I have x0 minus h divided by h x0 plus h. x0 minus x0, this will cancel. Then I have minus h divided by h's will cancel, and we end up with minus 1 divided by x0 plus h. Replace h by 0 now, and we get minus 1 over x0 squared. Picture looks like this. When x0 is 2, the slope, or the derivative at 2, using the formula, is minus a quarter. When x0 is minus 1, the slope, or the derivative, is equal to minus 1. If the derivative of f at the point x0 exists, then we say that f is differentiable at the point x0. If we have a function which is differentiable at every point, then there's a short way of saying this. We just say that the function is differentiable. If f is differentiable, then we have a new function, which we call f prime. F prime is called the derivative of f. Next example, let's suppose we're looking at the function x divided by x minus 1. Differentiate this function. That's another way of saying find the derivative of this function. We're going to use our formula, our definition. F prime of x is the limit as h tends to 0 of f of x plus h minus f of x divided by h. And the first thing to notice is that if we take our formula for f of x and we replace every x with x plus h, we get x plus h divided by x plus h minus 1, which is here. We have this minus f of x, or minus x minus 1, all divided by h. Using the same trick that we used last time, we can simplify this down to the limit of minus 1 divided by x minus 1, x plus h minus 1. Then it's okay to replace the h by 0, and we get the answer minus 1 divided by x minus 1 squared. Let's talk briefly about notation. If you look in different calculus books, you will notice there's lots of different ways to write the derivative of a function. So far, I've been using the notation f prime of x. You can also write y prime, or dy dx, or df dx, or d dx of f of x, or some people use y dot or f dot of x. Quick history lesson. Calculus was started by two men, Newton and Leibniz, and they both claimed to have invented calculus first. Then they argued about who invented calculus first, and then they ended up hating each other. So Isaac Newton, who is perhaps more famous nowadays, use the notation f dot and y dot. Gottfried Leibniz, who we now think is the one who invented calculus, used df dx and dy dx. The notation f prime and y prime, which I've been using so far, was introduced later by Joseph Louis Lagrange. Let's suppose that instead of just the derivative, we want to calculate, or we want to denote, the derivative of a function at a particular point, x0. Then again, there's different ways to write this. We might say f prime calculated at x0. We might write dy dx at x is equal to x0, or df dx at x is equal to x0, or ddx of f of x at x is equal to x0. For example, let's suppose we have the function u of x is equal to 1 over x. And let's suppose I want to calculate the value of this derivative when x is equal to 4. In other words, I want to calculate u prime at 4. That's the same as saying I want to calculate ddx of 1 over x at x is equal to 4. We've done this derivative. We know that the derivative of 1 over x is minus 1 over x squared. So this is equal to minus 1 over x squared at x is equal to 4. At this point, we can replace x by 4 to get minus 1 over 4 squared, or minus 1 over 16. For example, show that the absolute value of x is differentiable between minus infinity and 0, and between 0 and infinity, but is not differentiable at 0. First, let's look at this for x greater than 0. We're trying to calculate the derivative of the absolute value of x if x is a positive number. If x is a positive number, the absolute value of x is just the same as x. So we're calculating the limit as x plus h minus x divided by h. Simplify this, x minus x cancels, and then h divided by h cancels. We have the limit of 1, and the limit of a number, of course, is just a number, so is equal to 1. Similarly, if x is less than 0, the only change here is if x is a negative number, then absolute value of x is equal to minus x. For example, the absolute value of minus 3 is equal to minus 3, or 3. Then we can go through the same calculation, and we can find that the derivative is equal to minus 1. This shows that our function is differentiable on the open interval from minus infinity to 0, and on the open interval from 0 to infinity. But what happens at 0? We can try to do the same thing. The limit is h tends to 0 of the absolute value of 0 plus h minus the absolute value of 0 divided by h, which is the limit is h tends to 0 of the absolute value of h divided by h. But the absolute value of h divided by h is either plus 1 or minus 1, depending on if h is a positive number or a negative number. We have a function which is sometimes equal to 1, sometimes equal to minus 1. It's not always close to one particular number, so this limit does not exist. Because this limit does not exist, our function is not differentiable at 0. Here's a graph of the absolute value of x. The left part, the green part, has slope -1. The right part, the blue part, has slope equal to 1. And in the middle, at the red point, the derivative does not exist. We might then ask, when does a function not have a derivative at a point? If we have a corner like this, then the derivative does not exist. If we have a cusp, type of pointy corner, then again, the derivative does not exist. If we have a vertical tangent, if we try to calculate the limit function like this, the limit would be equal to -infinity. Whenever we have a vertical tangent like this, the derivative does not exist. If we have a discontinuity at x0, then the derivative does not exist. A different type of discontinuity, again, for this type of discontinuity, the derivative does not exist. Using this idea and combining it with an idea from symbolic logic right back at the start of this course. The idea was that P implies Q is the same as not Q implies not P. We're saying a function has a discontinuity, implies that a function is not differentiable. We can turn this around using this idea from logic and say a function does have a derivative at a point, implies that the function is continuous at this point. And that is the end of today's lesson. Next week, we will cover 5 chapters, 27 up to 31. When we know the midterm grades, after I finish reading them, I have 2 courses to read. I've almost finished reading the exams from the other course, and then I'll start reading your exam. Hopefully, in a week from today, I will have finished your exam. There was a question from earlier about a makeup exam. So the way this works is you need to ask your department or your faculty for permission to take a makeup exam. They will say yes or no to each student who applies, and then they will send me a list of students who they've given permission to. After I receive a list of students, I will arrange a makeup exam if we have one. If no students are given permission by your department or your faculty, then there's no need for a makeup exam and there won't be one. Are there any more questions? So, as always, this is your chance to ask questions if you have any. If you don't have any questions, then you're welcome to leave the classroom whenever you wish.